On September 5th, 1977, a rocket lifted off from Cape Canaveral, Florida, carrying something that no other machine in human history had ever carried before. It was not a weapon. It was not a satellite designed to beam signals back to Earth. It was not built to orbit the planet or photograph the weather or spy on a foreign power. It was built to leave the Earth, leave the Moon, leave every planet in our solar system, and eventually, if everything went as planned, leave the Sun itself behind, to cross a boundary that no human-made object had ever crossed before, and become the first physical thing built by human hands to enter the space between the stars. That spacecraft was Voyager 1, and nearly half a century later, it is still going. Right now, as you read or hear these words, Voyager 1 is approximately 15.8 billion miles from Earth. That number is so large, it is almost meaningless without context. So here's the context. If you drove a car at highway speed without stopping, no fuel breaks, no sleep, just continuous driving, it would take you roughly 17,000 years to reach Voyager 1. The signal it sends back to Earth, traveling at the speed of light, the fastest speed that anything in the universe can travel, takes nearly 23 hours to complete the journey. One way. If the engineers at NASA's Jet Propulsion Laboratory send a command to the spacecraft right now, they will not receive Voyager's response until almost 2 full days later. And by the time that response arrives, Voyager 1 will already be another few million kilometers further away than it was when the command was sent. By November 2026, Voyager 1 will reach a milestone that no human-made object has ever reached before. It will be exactly 1 light day from Earth, the distance that light travels in a full 24 hours. 1 light day. The engineers tracking it have already marked the date on the calendar, November 18th, 2026. When that happens, Voyager 1 will become the first thing ever built by human civilization to sit an entire light day away from the planet that built it. In the entire sweep of human history, from the first stone tools, to the first fire, to the first cities, to the first aircraft, to the first nuclear reaction, to the first moon landing, nothing we have ever made has traveled this far. And now, in a development that brings these 2 extraordinary stories together in a way that nobody fully anticipated, the James Webb Space Telescope has turned its instruments in the direction of interstellar space, the vast region where Voyager now travels, and what it has found there is changing what scientists thought they knew about the territory between the stars. To understand what Webb found and why it matters so much, you first need to understand what Voyager actually crossed when it left our solar system behind, because most people imagine space as a simple thing, a vast emptiness that begins where the planets end. But that is not how it actually works. Our sun, like every star in the galaxy, does not simply exist in a vacuum. It radiates. It constantly pours out a stream of charged particles, electrons and protons moving at millions of miles per hour in every direction, in what scientists call the solar wind. This solar wind does not just blow out into space and disappear. It pushes back against the gas of the galaxy itself, inflating a vast protective bubble around our entire solar system. That bubble is called the heliosphere, and it extends far beyond the orbit of Pluto, far beyond anything you've probably ever thought of as being part of our solar system. The heliosphere is so large that it took Voyager 1, traveling at roughly 38,000 miles per hour since 1977 until August 25th, 2012, 35 years after launch, to finally reach its edge and cross through. That edge is called the heliopause. It is the point where the sun's outward pressure and the pressure of interstellar space exactly balance each other. The border, the precise line where our solar system ends and the space between the stars begins. When Voyager 1 crossed the heliopause in 2012, it became the first human-made object in history to enter interstellar space. Not deep interstellar space, it is still within what astronomers call the Oort cloud, the vast and distant shell of icy objects that gravitationally belongs to our solar system and will for another several hundred years of travel. But interstellar space in the sense that matters most to scientists, the region where the sun's wind no longer reaches, where the gas and magnetic fields are no longer shaped by our star, where the environment is dictated by the galaxy itself rather than by the sun that gave us life. Voyager 2, Voyager 1's twin spacecraft, launched on August 20th, 1977, 2 weeks before Voyager 1, but on a slower trajectory, crossed its own section of the heliopause in November 2018. Together, these 2 spacecraft are the only human-made objects ever to have operated in interstellar space. They are the only direct in-situ data sources we have ever had from the region beyond the sun's protective bubble. Everything else we know about interstellar space has come from distant observations made by telescopes. And that is exactly where the James Webb Space Telescope enters this story. Webb launched on Christmas Day, 2021, riding an Ariane 5 rocket from a launch site in French Guiana, and spent the following month traveling to its permanent observing position, a gravitationally stable point in space called Lagrange Point 2, nearly 1 million miles from Earth in the direction away from the Sun. It is the most powerful space telescope ever built. Its primary mirror is 6.5 meters across, composed of 18 gold-coated hexagonal segments of beryllium, and it collects more than 6 times as much light as the Hubble Space Telescope, which spent 3 decades as the gold standard of space observation. But the most important thing about Webb is not its size, it is what it sees. Webb operates primarily in infrared light, wavelengths of light that are invisible to the human eye, but that carry a kind of information that visible light telescopes simply cannot access. Infrared light penetrates dust clouds that would block an optical telescope completely. It carries the chemical fingerprints of distant objects in ways that visible light does not. And crucially, it can detect the faint thermal glow of extremely cold, distant objects that would otherwise be completely invisible to any instrument humans have previously built. When Webb turned its instruments toward the interstellar medium, the name scientists give to the gas, dust, magnetic fields, and cosmic ray particles that fill the space between the stars, what it began to reveal was a landscape of staggering complexity that our previous understanding had dramatically undersold. For decades, the interstellar medium was described in textbook summaries as a thin, cold, relatively featureless void, punctuated by occasional clouds of gas and dust. The truth, as Webb's infrared eyes began to show, was considerably more structured and dynamic than that description ever captured. Webb revealed that the interstellar medium is threaded with an intricate architecture of filaments and sheets, long, thin structures of gas and dust that stretch across enormous distances and serve as the channels along which matter condenses and flows in the galaxy. These filaments are not static, they are dynamic. They interact with each other, with magnetic fields, with the shock waves from distant supernovae, in ways that regulate how quickly new stars form and how the chemical composition of the galaxy evolves over cosmic time. Webb has been able to image these structures in the infrared, with a level of detail that no previous telescope could match, revealing a universe between the stars that is not empty at all, but is, in a very real sense, alive with slow, vast, gravitationally driven motion. One of the most striking of Webb's contributions to our understanding of interstellar space came through its study of interstellar ice, the frozen molecules that coat dust grains drifting through the cold regions between stars. In 2023, Webb detected the coldest interstellar ice ever measured, in a molecular cloud called Chameleon Y, identifying frozen carbon dioxide, ammonia, methanol, and other organic molecules locked into icy mantles on dust grains at temperatures approaching minus 260 degrees Celsius, just a few degrees above the absolute zero point at which all molecular motion would stop entirely. These ices matter enormously for our understanding of how life's building blocks are distributed throughout the galaxy. The same kinds of molecules that Webb's detecting frozen onto dust grains in interstellar space are the precursors to amino acids, sugars, and other compounds that are essential to life on Earth. Webb is showing in real time that the raw ingredients for life are not rare or exotic. They are woven into the fabric of the galaxy itself. Then came the discovery that genuinely reordered the conversation about what interstellar space actually contains. In July of 2025, astronomers detected the third known interstellar object ever to pass through our solar system, a comet designated 3I Atlas. Unlike the first 2 interstellar visitors, Oumuamua detected in 2017 and still not fully explained, and 2I Borisov detected in 2019, the timing of 3I Atlas meant that for the first time in history, the most powerful space telescope ever built could be turned directly onto an interstellar visitor and analyze it in extraordinary detail. Webb observed 3I Atlas in August of 2025, using its near-infrared spectrograph instrument to examine the light from the comet's coma, the cloud of gas and dust surrounding its nucleus. And then in December 2025, after the comet had made its closest approach to the Sun and it was beginning to exit our solar system, Webb looked again, this time with its mid-infrared instrument, collecting what scientists described as the first mid-infrared chemical fingerprint of an interstellar object ever obtained. What they found was not what they expected. The chemical composition of 3I Atlas was significantly different from anything found in our own solar system's population of comets. The relative abundances of different molecular species, the specific mix of water ice, carbon dioxide, methanol, and other compounds, pointed to an origin environment that is genuinely distinct from the conditions in which our own solar system formed. Scientists describe the comet as material from a distant corner of the galaxy where the chemistry is markedly different from our own cosmic neighborhood. 3I Atlas was not just a comet passing through. It was a sample, a physical piece of interstellar space carrying the chemical signature of a completely different stellar environment, delivered directly into our solar system at exactly the moment when we had the tools to read that signature in full. But here's what connects all of this back to Voyager in a way that gives this entire story its deepest meaning. Voyager 1, right now, is traveling through the exact kind of environment that Webb is studying from a distance of nearly 1,000,000 miles. It is physically inside the interstellar medium. Its remaining instruments, a plasma wave detector and a magnetometer, the last two scientific tools still operating after a lifetime of gradual shutdowns to conserve power, are recording the properties of the space between the stars directly in real time as the spacecraft moves through it at 17 kilometers per second. What Voyager senses directly and what Webb sees remotely are two aspects of the same phenomenon. And when scientists combine these two datasets, they get something that neither instrument could provide alone: a ground-level view and a wide-field view of the same environment simultaneously. This combination has already produced surprises. The plasma wave data that Voyager 1 has been returning from interstellar space, a faint, steady hum first detected years ago and confirmed as the natural oscillation frequency of the interstellar plasma, suggested a density of electrons in the medium around Voyager that was slightly higher than older models had predicted. When Webb's observations of the broader structure of the interstellar medium near the heliosphere were incorporated into the models being used to interpret Voyager's data, the picture became clearer. The interstellar medium immediately beyond the heliopause, the region Voyager is currently traveling through, appears to be somewhat denser and more magnetically structured than the simpler models assumed. It is not a smooth transition from the solar wind to the interstellar gas. It is a complex boundary zone, layered, structured, and still in the process of being understood. There is something deeply moving about what this represents when you step back from the technical details and think about it in human terms. Voyager 1 was built almost 50 years ago. Its computers have 69 kilobytes of memory, less than a modern greeting card. It was designed for a 5-year mission to study Jupiter and Saturn. The engineers who built it expected it to fall silent long before it ever left the solar system. And yet here it is, still transmitting, still measuring, still sending back whispers of data across 15 billion miles of interstellar space. Its 22-watt radio transmitter, a signal no more powerful than a refrigerator light bulb, somehow reaching NASA's 70-meter dish antennas at the rate of 160 bits per second. For context, the slowest dial-up internet connection in the 1990s was thousands of times faster. And yet, that trickle of data, arriving from further away than anything humanity has ever reached, is still telling us things that we could not learn any other way. It carries something else, too. Attached to both Voyager spacecraft, selected by a committee led by the astronomer Carl Sagan, is a golden record, a 12-inch gold-plated copper disc containing sounds and images from Earth, music from across human cultures, greetings in 55 languages, including Sumerian, the oldest written language in human history, the sound of rain and wind and surf, the cry of a newborn child, brainwaves recorded from a human being thinking about their experience of being alive, a pulsar map that would allow any sufficiently advanced civilization that found the record to calculate the precise location in the galaxy from which it was launched. The golden record was never really meant to communicate with aliens, though the possibility was part of its design. It was meant to say something about us, about who we were at the moment we first crossed into the space between the stars, what we valued, what we loved, what we wanted to say to the unknown. That record is now drifting through the interstellar medium that James Webb is studying. It will continue drifting long after Voyager's last instrument goes silent, which scientists now estimate could happen sometime in the mid-2020s to early 2030s, depending on which components hold out longest. And it will drift for an almost incomprehensible time after that. The material the record is made from is stable enough to survive for hundreds of millions of years in the cold of interstellar space. In 40,000 years, Voyager 1 will pass within a few light years of a star in the constellation Ophiuchus, without slowing, without stopping, carrying its golden disk forward through the dark. And everything Webb is now teaching us about that dark, its structure, its chemistry, its ice, its filaments, its magnetic fields, is filling in the landscape through which this first messenger of humanity is quietly, endlessly traveling. When Carl Sagan described the famous pale blue dot photograph, the image Voyager 1 took of Earth from a distance of nearly 4 billion miles in 1990, showing our planet as a tiny speck of light suspended in a sunbeam, he wrote words that have become among the most quoted in the history of science. He described Earth as a mote of dust suspended in a sunbeam, our planet's apparent insignificance in the vastness of space, a reminder of our responsibility to be kinder to each other since there is no help coming from somewhere else, and since this pale blue dot is the only home we have ever known. What James Webb is doing, by studying the interstellar space into which Voyager is now sailing, is extending the reach of that perspective. It is turning the most powerful set of eyes we have ever built toward the territory that only our most distant machine has ever physically touched. And what those eyes are seeing is not an empty void. It is not a featureless darkness. It is a structured, chemically rich, dynamically evolving environment, threaded with ice and magnetic fields and slow rivers of gas, a galaxy between the stars that is as complex and layered and surprising as the stars themselves. Voyager 1 will be a full light day from Earth by November 2026. That is a number that should stop you. Not metaphorically, but actually stop you and sit with the reality of what it means. A light day, the distance light travels in a full day. The fastest thing in the universe, running without stopping for 24 hours, and still only barely reaching where a spacecraft that left Earth in 1977, carrying a phonograph record and a camera and a suite of sensors designed to last 5 years, has managed to travel under the power of a rocket built by human beings half a century ago. And it is still going. And James Webb is watching where it goes. That is the story. Not just of two machines, the space between the stars. It is the story of what it means to reach, to build something fragile and finite and send it in a direction that nothing built by hands has ever gone, and then to build something else, decades later, more powerful and more precise, and to watch where the first thing went. Together, Voyager and Webb represent the two poles of what humanity is capable of doing when it decides to try to understand something larger than itself. One is brute persistence, a 50-year journey on a one-way ticket, still transmitting a faint heartbeat across distances that language barely handles. The other is acute perception, an eye tuned to wavelengths of light we cannot see, peering into the cold dark of the galaxy with a sensitivity that would have seemed impossible to the engineers who launched Voyager in 1977. And what they are finding together is that the universe between the stars is not an ending. It is an environment, rich, structured, full of the chemistry from which stars and planets and perhaps life will one day form. The pale blue dot is still there, still tiny, still suspended in its sunbeam. And the golden record is still sailing outward into a galaxy that James Webb is only beginning to show us.